In this little video, we will look at Raoult's law, which applies to ideal solutions, and Henry's law, which applies to dilute solutions. We have already shown that for an ideal gas, the chemical potential is given by the standard chemical potential of the gas plus RT multiplied by the logarithm of the partial pressure of the gas. We will now look at liquid vapor equilibria. This is a closed container containing liquid A. So this is liquid and this is vapor. And some of A has vaporized to create some pressure in the vapor phase, which we call PA star. Star here denotes pure substance. At equilibrium, the chemical potential in the liquid phase and the vapor phase must be the same. So we can write that the chemical potential of pure A in the liquid phase is equal to the chemical potential of A in the gas phase. You can use the parenthesis gas plus RT log of PA, and now we have a star because this is pure A. So PA star is the vapor pressure of A. Now if a second component is also present in the liquid phase, we have both A and B. So in the vapor phase, we have both a partial pressure arising from A and a partial pressure arising from B. Then this equation changes, and now we have the chemical potential of A in the liquid phase. Now there is no star because B is also present, so it's not a pure phase anymore, is equal to the chemical potential of A, the standard chemical potential of A, plus RT multiplied by the logarithm of the partial pressure of A. If we call this equation 1 and we call this equation 2, we can eliminate the standard chemical potential of A. And if we do that, we will get the chemical potential of A equals the chemical potential of pure A minus RT logarithm the vapor pressure of A plus RT logarithm the partial pressure of A. And then this equation becomes that the chemical potential of A is equal to the chemical potential of pure A plus RT logarithm of the partial pressure of A divided by the vapor pressure of A. Now what we really want to know is how the composition in the liquid phase here affects the partial pressures or the vapor pressures in the gas phase or in the vapor phase. So there was this chemist Raoult who did a lot of experiments on closely related liquids. So liquids which interact similarly to each other, for example, one can think of benzene and toluene. Must be fairly similar. And he found that the partial pressure of one component in the vapor phase is proportional to the mole fraction of that component in the liquid phase. Remember, Xa is the mole fraction of that component in the liquid phase and not the vapor phase, multiplied by its vapor pressure. So the partial pressure of A is equal to the mole fraction of A in the liquid phase multiplied by the vapor pressure of pure A. Let us try to plot this pressure. So on the x-axis you have the mole fraction of A, which goes from 0 to 1. So when the mole fraction is 1, you have pure A, so the pressure is the vapor pressure of A. When the mole fraction of A is 0, you have pure B, so the pressure is the vapor pressure of B. And since this is an ideal solution, the pressure will decrease linearly. This is the total pressure. and the pressure of A increases from 0 to 1 as we increase the mole fraction from 0 to 1, and the pressure of B decreases from PB star to 0 as we decrease the mole fraction of B from 1 to 0. So this is a graphical illustration of Raoult's law, and one can show, well, this is of course true, that the total pressure is equal to the mole fraction of A multiplied by the vapor pressure of A plus the mole fraction of B multiplied by the vapor pressure of B. This arises from simply that the pressure is equal to the partial pressure of A plus the partial pressure of B. And then one can substitute this equation into the previous one, and then one obtains the condition for an ideal solution, which is that the chemical potential of A is equal to the chemical potential of pure A. So on the left hand side is the chemical potential of A in a mixture, on the right hand side is the chemical potential of pure A plus RT multiplied by the logarithm of the mole fraction of A. This is the definition of an ideal solution. So in this case, both A and B follow Raoult's law. For real solutions, the situation is a bit different. A scientist called Henry measured the partial pressure of the solute, which we call B now. So for the remaining part of this video, solute is equivalent to the component B. And he showed that for dilute real solutions, the partial pressure of B of the solute was still proportional to the mole fraction of B of the solute in the liquid phase, but now the proportionality constant is not the vapor pressure of B, but something called the Henry's law constant. And there are various methods, various ways of writing this equation, but this is Henry's law. So to illustrate this graphically, let's plot the mole fraction of B versus pressure. So here you have the mole fraction of B, which is the solute. When you have only B, then the total pressure must be the vapor pressure of B. In the case of an ideal solution, this would increase linearly. In the case of a real solution, this curve looks approximately like this. And at low XB, so at low mole fraction, so in the dilute solution regime, this line is linear. This tangent at low XB will hit the y-axis at a point which will be equal to KB. So one can again do a simple liquid vapor equilibrium for B. So the chemical potential of B in the liquid phase must be equal to the chemical potential of B in the gas phase. And now we can replace PB by XB multiplied by KB. So this can be written as the standard chemical potential of B plus RT log of the mole fraction of B multiplied by Henry's law constant. And now remember that log of A multiplied by B is equal to log of A plus log of B. So we can simplify the above equation and write it in the following way. This entire thing here is a constant, and this can be called the chemical potential of pure B plus RT multiplied by the mole fraction, logarithm of the mole fraction of B. So this comes from Henry's law. Let us make this a little bit simpler and more interesting, in particular for biological systems. Now we want to relate this mole fraction to the concentration, because it is difficult to measure mole fraction, but it is easier to measure and control concentrations in solutions. The mole fraction of B must be proportional to the concentration of B in the solution. And this can be written as the mole fraction of B is equal to some constant K1 multiplied by the concentration of B. And then I can multiply this by a standard concentration and then divide this by a standard concentration. And this whole thing is now another constant, so let's call that K2 multiplied by the concentration of B divided by a standard concentration. This we can substitute into the previous equation, and now we get the chemical potential of B in the liquid phase is equal to the chemical potential of pure B plus RT logarithm of K2 concentration of B divided by a standard concentration. And the standard concentration, as it turns out, is equal to 1 molar or 1 molal, depending on what units you are using. So one can write this as remember that the standard concentration is equal to 1. And I can expand this further like I did in the previous case and write this as RT log of K2 plus RT log of the concentration of B. And now this whole term can be written as some standard chemical potential of B plus RT log of the concentration of B. So for a dilute solution, this is the expression for the chemical potential of B in the liquid phase. If you were to measure the differences in the chemical potential in the liquid phases in, for example, 2 separate compartments, you could write mu B1 in one compartment minus mu B2 in the separate in a different compartment, and this would be equal to the standard chemical potential of B plus RT log of the concentration of B in the first compartment minus the standard chemical potential of B minus RT log of the concentration of B in the second compartment. So the difference in chemical potential between the two compartments is the concentration of B in one compartment divided by the concentration of B in the second compartment, the logarithm of this multiplied by R multiplied by T.